Okay, welcome everyone. Another edition of Symmetry in Newcastle. Today's speaker, or the first speaker of today, is Paul-Henri Leemans from University of Neuchâtel in Switzerland. And here I feel compelled to mention that in French, Neuchâtel means Newcastle, so he's partially a domestic speaker. If you have any questions during the talk, either feel free to politely interrupt our speaker or just put them in the chat. I will see the chat and I will ask them on your behalf if you're too shy.
Okay, perfect. Thank you for the invitation. So as you can see, I'm going to speak about Cayley graphs and their automorphism groups. Okay, this is a joint work with Michael de la Salle. Apparently, it is recorded on YouTube, but if you want to have the slides, you can find it on my website. Okay, so it's a subject that is at the intersection of geometric group theory and combinatorics, especially graphs, and also probability and random walks. Not for the main part of the subject, but for the tools. Okay, so in group theory, sometimes we want to speak about representation of groups. A classical representation of groups is just an homomorphism from G to GLV, where V is some vector space. But you can ask for more. You can ask, for example, to an homomorphism for G to the automorphism of some space with good properties. In my case, I'm interested in graph. So, and especially not any homomorphism, but isomorphism. I really want to represent some group as the automorphism group of a graph. So the first, definition of a graph, it's pretty straightforward. You have some vertices and some edge between them. And we will be interested in connected graph, and more specifically in locally finite connected graph. So locally finite means that at each vertex, you have only a finite number of edges that are adjacent to this vertex. Okay, so the first naive question is, what are the finitely generated groups that can be represented as the automorphism group of some graph? And it turns out that every group is the automorphism groups of some graphs, at least for finitely generated ones. And this is an old result due to Grrr and Salle. So the next step is, okay, maybe we want to have a graph, but not any kind of graph, with a little more structure on the graphs. So we can ask, for example, the ask to be regular. That means that the action of its automorphism groups is both free and transitive on the vertices. That is, for every pair of vertices, you have exactly one element of the automorphism groups sending V to W. Okay. So the main question now is, what are the finitely generated groups that can be represented as the automorphism groups of some locally finite graphs with the requirements that these automorphism groups act regularly on the graph? Okay, so it turns out that in this case, your graph X will be a Cayley graph of G. This is a result due to Salle. Okay, so this question was solved for finite groups in the 70s. It took some time to a lot of mathematicians. And also during the 70s, it was solved for free products of finitely generated groups. But after that, people don't know that much on infinite groups. And last year, we finally solved it with Michael de la Salle, using tools that are not the same as the tools that were used for finite groups. Okay, so I'm going to remember quickly what is a Cayley graph. I suspect that all of you know what is it, but I need some technical definitions. So you take a group G and a generating set S, and the corresponding graph, you will have vertices. So it will be G, and for every element of your group and every generator, you will have an arc labeled by S from G to GS. So it means that if you have G and GS, you have both an arc, so directed edge from G to GS, and an arc in the other direction. And so an edge is simply a pair of two arcs, one going in one direction and the other going in the other direction. Okay, so classical example, you can look at the Cayley graph of the integer with standard generating set. This is just a line, but you can take other generating set if you want. And it's not important for us, but if you take finite generating sets, the graph you obtain will be quasi-isometric. So they are not the same, but they look like the same. Okay, so quick reminder, each edge on a Cayley graph consists of a pair of arcs. Each arc has a label, which is an element of the generating set. And each edge has a color, which consists of a pair of elements of the generating set. So when I draw the line for the Cayley graph of Z, it's really, you can go right by doing +1, or you can go left by doing -1. It's an easy exercise to see that your group G acts on its Cayley graph by left multiplication. So you have a graph and you have three distinct automorphism group of your graph. You have the whole automorphism group of the Cayley graph. You have outcall, which is the automorphism group of the Cayley graph that preserves the color. So that means if you will send edge to edges with the same color, and you are a smaller group, which is outlab, which preserves the labeling. And it turns out that this small group is exactly G. It's, again, an easy exercise to check that. So for Z, we can just some example. So as I said, since it's a Cayley graph, the small group is Z. If you just ask to preserve the colors, and it's an infinite diagonal group, because you have the switch, you can reverse the orientation, and the full group is still the diagonal group because there's only one color in this case. So another example for this square, the grid. So once again, the smaller group is this square. It acts by translation. This times, if you have a bigger group, if you want just to preserve the color, because you can switch either the blue edge, change the direction, or the red edges. And the full group, you can also send red edges to blue edges, and so on. So we have three distinct groups in this case. Okay, so in this context, if you want to construct the full automorphism groups, a classical tool is you start with your graph, which you know that you have a subgroup isomorphic to Z. So in this case, a line, and you add some decoration to kill extra automorphism. So if we want to look at the example for Z, you just add this kind of decoration, which will forbid to have a switch, and you would add it everywhere. So now it's an exercise to check that this new graph has automorphism groups exactly Z. And okay, it's not working. Okay, yeah. And you can try to do the same exercise with this square and so on. And in fact, it is the idea behind the fact that for every finitely generated group, you can find a graph which has this automorphism group. You just start with a Cayley graph and you add some decoration. But as you can see, the graph I obtain is not regular. I mean, we have vertices with degree 4 and vertices with degree 3, so the automorphism group is not going to be transitive. So it's something, but it's not that we want. So if I recast the main question, we are looking for finitely generated group G, such that there exists a finite symmetric generating set S with G is equal to this automorphism group. So here, when I put equal, is not only isometric, it's really equal. You have an unbundling of G in the automorphism group, and you ask this unbundling to be surjective. Okay, so when this happens, we say that the Cayley graph is a graphical regular representation, and that the group is rigid if you can find such graphical regular representation. So first, non-example of such groups. it is easy to check that if you take an abelian group that is not isomorphic to z over 2z at some power, then it is not rigid. Why? You look at the map, the inverse map sending g to g minus 1, and it is in fact an automorphism group of the Cayley graph that not comes from a translation. And okay, this is why we need the abelian group to be not equal to z over 2z to some power, because otherwise this map is just the identity. Okay, so there is another infinite family of counterexample. If you know it, fine, but otherwise it's not important. They are called generalized dicyclic group and are extension of degree 2 of abelian groups. And you can check that these groups are not rigid. So the main example in this family is a group of quaternion. Okay, and apart that, you can check by hand or with a computer that there are 13 exceptional groups, small groups of order at most 32 that are not rigid, neither in one of the above family. So these examples was found early, and people asked, are these the only example of non-rigid groups? And it turns out that it is a fact. So this is a big theorem for finite groups that if G is neither one of those counterexamples, then it is rigid. So the main problem with this, okay, it's not a problem, but with the proof of this theorem is that it's not an unified construction. You have to do a lot of bits and cases, and it's really hard and asks a lot of effort to do it. Then Watkins also shows that if you take a free product of finitely generated groups, then your group is rigid. Okay, and okay, there is a problem. But, and the construction for finite group use strongly the fact that G is finite. For example, you use Weiss Thompson. And for some variation of the main question, you also use the classification of finite simple groups. So it's not the statement, but the proof really goes down to the fact that J is finite. So when we want to look at infinite groups, you have to find new ideas. Okay. And there is also some sort of asymptotic results saying that if some family of finite group, specifically an important non-abelian finite group of even order, then almost all Cayley graphs are GRR. So at first, it seems difficult to find graphical regular representation for a group, but in fact, you can take any symmetric generating set, and it will do the job. I mean, probably. Okay, so our main result with Michael was the fact that these statements remain true for finitely generated infinite groups. So the statement that your group is either abelian or generated dicyclic or rigid. Okay. Moreover, the proof is constructive. So if you give me any finite generating set S, I can show you explicitly some generating set T, such that the Cayley graph is a GRR. And moreover, we have a control on the size of T. So we have an explicit function F saying that the set T is not too big. Okay, so the main problem is that the function is explicit, but it's an exponential and it grows really fast, but still we have a bond. And oh yeah, just to be correct, when I said I can explicit UT is, if you want the construction to be really explicit, you need an oracle that solves the word problem in your group. But still, we have the existence. Okay, so what are the nice thing about this proof is that more or less we have only a unique common structure for the proof. Just at the end of the proof, we do a dichotomy, but still. And the proof also works for finite groups with an element of big order. So here big depends on the rank of G. And it's explicit, but it's really big. And in particular, if we obtain that for every n, there exist only finitely many exceptional groups of rank n. And in fact, it's nice because in the subject of rigid group graphical regular representations, there is some variation, and for all these variation, you always have one or maybe two infinite family of counterexamples that are pretty straightforward. You have some exceptional groups of small orders that don't work, and all the other one are working. So here you have kind of explanation what it happens like that. The fact that the proof also works for finite groups. Okay, and yeah, it's not an asymptotic per se, this result, but it's some sort of weak form of asymptotic that's saying that if you start with any generating set S, you're going to find the bigger set T that works. Okay, so now a word on the proof. So short reminder that we have these three automorphism groups of our graph. And we're going to start with some generating S, set S, and construct some bigger T and checked separately that these two inequalities are in fact equalities for T. Okay, so this is done in three propositions. So the first one is saying that if G is neither generalized acyclic nor abelian, then for every generating set S, we can find a bigger T such that this group, automorphism that preserves the color of the Cayley graph, also preserves the S labels. That means if you look at automorphism of your Cayley graphs, sending every edge labeled by T, every arc labeled by T, either to an arc labeled by T or to T minus 1, then if your arc was labeled by S, it's going to be sent to an arc labeled by S for small s in big S. So maybe you can switch labels of arc for some T in the big generating set, but you're going to fix the S label. So the second proposition is the other inequalities, is that if you start with a generating set T, finite, then you have a bigger generating set U, still finite, such that the whole automorphism group of the Cayley graph preserves the T color. And so the last proposition saying that if you cumulate these two steps, start with S, find T, and then find U, then your Cayley graph is going to be a GRR for G. So just a word here. So for the first proposition, the hypothesis is that the group is neither generalized acyclic nor abelian, but we do not ask G to be finitely generated. And for the second proposition, we want G to be finitely generated, but it can be either dicyclic or abelian, it's not a problem. Okay, so first, going to give a short proof of proposition 3, that these two steps are enough. So you start with an element of your big automorphism group. You know that it preserves the colors, so you have your big graph with edge etiqueted colored by U, and you know that you preserve the T color. So if you look at the smaller graph where you remove all edge that are in U but not in T, phi is still an automorphism of this graph, and it preserves the color. So by the first proposition, doing the same, phi is an automorphism of the Cayley graph of G with respect to S that preserves the labeling. So you know that on vertices, you're going to act like translation by an element of G. This is true also for arcs labeled by S. And so you have the whole proof, but the idea is that still S is generating. It's enough to know that you act as like translation on vertices on arcs labeled by S. So the automorphism preserves all the graph. Okay. So now for the proof of proposition 1. So we have a group G and we have a generating set, and we want to find a generating set T with good properties. And in fact, it's really explicit. You just take elements that can be written as words of length at most 3 in your original generating set T. And we're going to prove that these generating sets do the job. So we look at the subgroup of automorphisms that fix the vertex 1G. And you can you have a bijection between this automorphism and bijection from from G to G, satisfying some algebraic condition, and then you do a lot of combinatorics. It's not pretty, but it works. And at the end, you find that if your subgroup H does not fix pointwise S, then G is either abelian or generalized cyclic. The important part of the proof is that the quaternion group Q8 plays a central role. For example, you're going to do some cases, and at some point you will find that your group is direct product of Q8 with 0 over 2z or a power of 0 over 2z, and such groups are generalized cyclic. So I'm not going to say any more about this because it's really combinatorics and it's not pretty to read. So now for the maybe more interesting parts, is the proof of proposition 2. We need geometric invariants to recognize colors of edges, and this geometric invariant is going to be triangle. So if you have an edge colored by some generator and this inverse, and an edge colored by some other generator, an easy way to distinguish them is to count the number of triangles in which they belong in the graph. So we define triangle SS to be the number of triangles in the Cayley graph containing this edge. And it really depends only on the color of the edge, not on the starting vertex, neither on the direction. That means if you have S or its inverse, they belong to the same number of triangles, of course. And it's immediate that if S and T does not have the same number of triangles, then you cannot send one to the other by an automorphism of the graph. So what we are going to do is, given some finite generating set S, we will construct a bigger T such that for every newly added generator, they're going to belong to at most 6 triangles. 6, it's not important, but what is important is that all generators are going to belong to at least 7 triangles. That is more than the new one. So this allows to distinguish in a geometric way between old and new generators. And we will also be able to characterize really all generators. So we ask that if you have 2 old generator, then and that they have the same number of triangles and they are the same, maybe or the inverse. So if we're able to find such T, this will be the end, because for such a T and an automorphism of the Cayley graph with respect to T, it's obvious that it's going to preserve the S color. Okay, so in order to do that, we need some technical lemma, and we are going to augment the number of triangles to which belong some elements S, not one at a time. So you have your finite generating set S, consisting of elements S1, S2, and so on. We will augment the number of triangles to which belong S1 to be at least 7. Then we will augment the number of elements to which belong S2 to be at least 7 and distinct from the number of elements for S1, and so on. So we will treat generators one at a time. Okay. So proof of this technical lemma. You start with an element of your generating set S, and we will look at some new generating set S, so SG. So you add a new element G, and you add G minus 1 S in order to have a new triangle. So you can do that for every G, and we want to find such Z with good properties, meaning that we're going to really augment the number of triangles to which belong S. So G need to be a new element. We need that G belongs to at most 6 triangles in the new graph, and so on for G minus 1S. And we also need that by doing that, we augment only the number of triangles to which belong S and not the other generators to keep the procedure local. Okay, so you can write down what means this condition from an algebraic point of view. For example, since we want to augment the number of triangles of S, it's enough to ask that G and G minus 1S are not in your first generating set in order to really add a new triangle. And you have a finite number of conditions of this form, G not in S, S minus 1, G not in S, and so on. So at the end, you have a finite set, F, such that if G, S minus 1, G are not in F, and the square are not in F2, then your new generating set SG works. So the main problem here is that the square map. Otherwise, it will be easy to find G such that G is not in your finite set, since your group is infinite. So I will denote by SQ the square map. And so we can do square root, meaning that elements such as the square belongs to system. Okay. And now we do two cases. Either you have an element of infinite order, or you are not virtually abelian. So virtually abelian, I believe that everybody knows the signification. It's that you have a finite index of groups that is abelian. And these two cases you can cover everything, because if you're finitely generated and not virtually abelian, then you have an element of infinite order, or you are finite. Okay. So the difficult case maybe is that if you have an element of infinite order, so okay, maybe not difficult, but the first case at least. So you start, you know that in your group you have an element of infinite order, G0. And instead of looking at generating set SG with G any element of the group, we are only going to look at generating set SG with G in the cyclic subgroup generated by G0. It is nice for us because in Z, every element has at most one square root. So the square map behave well in Z or in big cyclic groups. So knowing that, there exists infinitely many elements G in G0 such that the conditions are satisfied. Not all of them, but 3 of the 4 conditions, meaning that G and S minus 1 G are not in F and G square is not in F. If you are clever and you work more, you obtain the desired result with some small caveats. Is that meaning when augmenting the number of triangles for your generator S, you might also augment the number of triangles to which belong the generator S square. And since we didn't choose our generating set S, but we start with some generating set, it may happen that in your generating set you have an element S and its square. So it's a little problem. But it's not a big problem because you can say, okay, I'm going to first apply the lemma to augment the number of generators for S, and then apply the lemma to S square. So, okay, maybe when I do it for S, I augment S square, but I don't mind. I'm going to change S square later, and everything works fine. You just have to be a bit careful if you have a chain of elements S, S square, S4. and then go back to S. For example, if S is of order 3. But you can manage to do it. Okay. So now for the second part of the proof, so of the dichotomy, this time we start with a group that is not virtually abelian and some finite subset F. The main problem here is that it may happen that even if F is finite, then its square root is infinite. So you cannot use the Hilbert strategy like that. So for this part of the proof, we'll need a proposition that says that if you're not virtually abelian, finitely generated, you pick any element and every finite subset, then when you remove to G the square root of F and it's translated by some S, then you still have infinitely many elements. So, okay, maybe F is infinite, but it's not too big compared to the side of the group. Okay, so yeah, and so the direct corollary of proposition 4 is that it's possible to find G that works for our purpose. Okay, so in order to prove proposition 4, we will use 3 ingredients. The first one is that if you are finitely generated and you have element of, and every element has order 2, then G is finite, so it's easy to see that. Then we are going to use a lemma due to Dickmann about normal subgroups. I'm going to state it in a few minutes. And this is the part where we use random walks on groups, especially a result due to Tone. Okay, so the lemma due to Dickmann is that if you take any group with no condition on it, you take a finite subset such that two things. So you ask every element of F to be a finite order and also your subset to be invariant by conjugation. Then the normal subgroups it generates is finite. Okay, and so an easy corollary of this lemma is that if you take a finitely generated group, then G is finite if only if it has finitely many squares. Okay, just to prove to see a little bit. It's easy. You start with the number of with the square root of G. It's closed under conjugation. And if it is finite, then it contains only element of finite order. Then you look at the quotient. It's a finitely generated group. All of its elements have order at most 2, so it's finite. And since the normal sum group was also finite, then you can conclude that G was finite. And the other direction is obvious. I mean, if G is finite, it's going to have only finitely many squares. Okay, so now the hard part of the result is where we're going to do random walks of groups. So if we have a group G and we have some finitely generating set, we will ask this set to contain 1. It's important at this point. So you can look at the random walk on the graph. So what is it? You take the uniform probability of choosing an element in your generating set, and you do the random walk accordingly. So for example, on Z, at the first step, you start at 0, and you can go either to 0 with probability 1/3 or to +1 or -1. And then on the second step, and third step, okay. So the theorem of Tone we will use is if you start with a finitely generated group with a finite generating set symmetric containing 1, and you take 2 independent realizations of this random walk. If your group is not virtually abelian, then the probability that 2 elements commute is 0. So it's an interesting result because saying that if you sample 2 elements in non-virtually abelian groups, then they're never going to commute. Okay, and we will use that. So what we proved with Michael is that under the same hypothesis, if G is not virtually abelian, then the probability of one element to be of order 2 is small. Okay, it's not a direct corollary, but it will use the result of time. And with a little more works, you can prove proposition 4. Okay. And yeah, the main idea to prove proposition 4 is that if you have two elements which are both of order 2, and such that their product is also of order 2, they commute. So here is the link with the result of Thornton. Okay. Maybe now just saying something about variation of some main results. So we ask about automorphism of Cayley graph, but you can ask the same question if you look not Cayley graph, but Cayley D graph. So you start with a generating set that is not necessarily symmetric. You define your D graph in the same way we define Cayley graph. So you're going to have arc, but sometimes you have an arc in one direction, but not in the reverse direction. And you can ask the same question. What are the finitely generated groups G, such that there exists a finite and generating S with G equal to the automorphism group of the directed Cayley graph? So the name is directed regular representation. And it's easier to find such a graph because if you have a GRR and for each edge, you return only one arc, then it's going to work. It works for every finite groups with only 5 exceptions. This is due to Babai. Then Babai also shows that it works for infinite groups, but the proof of Babai always gives you an infinite generating set. So it's not really what we want because we are speaking of finitely generated groups. So we would like to have a locally finite graph, so a finite generating set. In fact, the proof we did with Michael for GRR, the same proof works for GRR. So with no modification, you obtain the same result. And one last question related to this is if you want to find some special kind of directed graph, which are called oriented graph by Babai. It means that for generating set S intersection with the inverse of S is empty. For the graphs, that means that you don't have bygones. If you have an arc in one direction, you can go back in the other direction. Okay, so this question was asked in the 80s by Babai and answered recently for finite groups. So we have an obvious family of counterexamples that are generalized D-Edward groups because in any generalized D-Edward groups, every generating set contains an element of order 2, so it's not going to work. But apart series, every finite groups works except for a small number of exceptions. So this is due to Morris and Spiga. And in fact, the proof we did with Michael also worked for this case. So we obtained that every finitely generated infinite groups that are not generated D-Edward admits such a graph. And here, just a small word on the proofs of Morris and Spiga. They used the classification of finite simple groups. So they need to use really strong tools in order to do that. Okay. Maybe a few words on other consequences of these results. So we obtain that every finitely generated groups has a locally finite Cayley graph with a countable group of automorphisms. So this is obviously true for groups that are rigid because the group of automorphism is G itself, so it is countable, and it's easy to show that it works in the general case. So And we also answer another question of Michael and Romain Tessera. So I need one last definition for this. We say that a graph X is local to global rigid if there exists some integer R, such that if you have a graph Y that looks like X on balls of radius R, then X covers Y. And as a corollary of our result, we obtain that every finitely presented group admits a locally finite, local to global rigid Cayley graph. And in fact, it turns out that it is a complicated classification, characterization of finitely presented groups. That means a group is finitely presented if only if it admits a locally finite, local to global rigid Cayley graph. Okay, and I'm saying I'm done. Yes, that's all. So if you have questions.
Thank you for the talk, Paul-André. So are there any questions for our speaker? Well,
I have a question about this last result. Is this about, that's a really cool animation, by the way. I really like it.
So
I imagine this has, yeah, I imagine this has to do with, you know, the whole thing about there being a certain ball of a fixed radius. I guess you could view this as, you know, finally presented groups being, what was it, isolated points in the space of marked groups or something like that. Is this some property? I guess you can translate this.
Maybe I didn't think about it, so I cannot answer,
Okay.
but yeah, maybe. At least it's a good question.
I had a question too, if I may. So you're so you're looking for GRRs for finitely generated groups. I was at some point interested in sort of an opposite question, namely, for which finitely generated groups is there a generating set such that the automorphism group of the corresponding Cayley graph strictly contains the group? So it seems that this should be true for most groups, that you can pick a generating set such that the automorphism of the Cayley graph is bigger than just the group itself. But I'm wondering if you know anything about, which classes of satisfy this property.
No, I didn't think about the question. About the thing that I can say to you is this asymptotic result from, I think, Babai and Godsil, I'm not sure of the name, saying that for some class of groups, nilpontents, non-abelian, and so on, for most generating set, it's not going to work. So
it's going to be, what is going to work? It's going to be a GRR?
What you want. So for most generating sets, as the automorphism group of your Cayley graph is going to be G itself. So not what you want, but it's for most.
Most, yeah, and it may be for all, even in some cases, I assume.
Yeah, maybe. Okay, so I skipped the result, but there is this authentic result, and I don't think that people ask the question in the other direction.
Yeah.
In fact, for finite groups, people try to, if for abelian and generated cyclic groups, people try to find graphs with the smallest automorphism groups. So we know that it's not going to be G, but in most time it's going. You can find a graph which G is index 2 subgroups of the automorphism groups.
Yeah.
So people are really interested in this direction, and I'm not sure that anybody apart you asks the question in the other direction.
Yeah, I would like the automorphism group to be big so that, you know, if it's an infinite graph, it may become non-discrete even.
But Stefan, there is an easy way to get, for any group G, you just take all but the non-identity element.
Okay, yeah.
And the Cayley graph from then is complete, and then you have many automorphisms, but that is perhaps cheating.
Yes, it is.
Yeah,
okay, I want a locally finite graph.
Yeah.
Thanks. Yeah.
I had a question about what does it mean? There was this result. I think this was this bye-bye. Okay, yeah. What does asymptotically almost all mean? Like what?
Okay,
How? Which probability measure are you using?
Okay, so then there is a precise statement, but I don't remember the constant, but saying that you look at all group of order n, and you look at, depending on n, almost all generating sets are going to work. So you have a function depending on n that if you take a group of order n, it's going, and you choose a generating set uniformly for finite groups among symmetric generating set, then all of them, unless at most f of n, are going to work, with f of n going to 0, with n going to infinity.
Mm-hmm. Right, but I just noticed this is for nilpotent because I thought, how are they working this out for all groups?
No, it's only for nilpotent, and so people are trying to solve this question for bigger class of groups, but there are no real results about that.
Okay. Do we have any further questions for our speaker? Well, if not, let's thank our speaker one more time. And we will reconvene in about 30 minutes with the next talk.